Okay, so let's talk assessment plan. So you guys know that the way that the grade is structured, you're like, where the heck is my grade? And we've talked about this a little bit, right? That you're getting these 9s, 7s, and 5s. But we've only done one assessment over each of the standards that we've covered so far. So we are due pretty soon here for a second round of assessment. So this is what I want you to know is kind of coming up and to be aware of what's happening. And as I've told you guys before, if we need to adjust a day or so, like I'm fine with that. I just don't want to overwhelm you or take too long on things. So today we're going to start standard 2.2, which is all about the first law of thermodynamics. Woohoo! We're not actually going to get to the first law of thermodynamics today, but we'll get there in a few days. The 2.2 standard is going to last, probably from about today through, I'm guessing, Tuesday or Wednesday of next week is my guess. If that's true, we would review, we're going to quiz the day after. So my anticipated plan is that we will quiz over 2.2 next Thursday. Another kind of short quiz, right? Not super overwhelming, kind of like we did yesterday. And then Friday would be a full-on review day, an opportunity to make corrections if you wanted, an opportunity for those things. And then the following Monday, which would be, let's take a peek here, the 25th of October. So Monday, October 25th, I anticipate would be our midterm. Midterm is being used very loosely. Obviously, it's not at the middle of the term, but it's kind of a big assessment in the middle of the trimester. Now, I don't know if October 25th is a good day, if that's a terrible day. So think about that. Let me know if you hear that there's lots of other stuff going on. I want to know that. But I want to tell you what's going to be on that midterm so that you can start to kind of be thinking about this. So we have done, let's see, 1, 2, 3, 4. This is our 5th standard. So we did 1.1, which was density. 1.2 was buoyancy. 1.3 was fluids flowing. Okay. And then 2.1 is what we just did. That was the ideal gas law. And 2.2, as I said, was the first law of thermo. So you are going to have free response questions and or ranking task type problems. This will not be multiple choice. It will be all work out kind of problems. It's not going to be like 5 questions because 5 free response questions is going to take longer than a period. But they will be broken out so that I can assess all 5 of these standards. But that's what we're looking for. So like free response or ranking task type things on that test on the 25th. Does that make sense? The other thing that I want to let you know is that if you have earned a score of a 5 on any of these quizzes, besides 2.2, because we haven't obviously done that one, I really, really want you to come in prior to next Monday. So that means you have a whole week, okay, to come in to make those corrections. Why? Because the reason to make corrections is not to improve your grade, although that's a nice added bonus. The reason to come in and make corrections is so that you can sit down and think about that material and deal with it and understand it, okay? So I'm going to give you 2.2 back today at the end of the period, but you know what you got on all of these, okay? So again, if you got a 7 or a 5, you can make corrections. 5s, you got to come in, okay? You've got to come in to make those corrections. On your time, you let me know if you want to sit down with me. I can do it during Liberty time. I can do it 5th hour if you're available. I can do before school. Let's make arrangements and find a time to do that, okay? This has got to be a priority. Does that make sense to everybody? Do you guys have any questions about this plan? Yeah.
How do we know if we got a 5?
So it's what it would have said, like your score on the quiz. It's in Infinite Campus. Yeah, they're in Infinite Campus. And I've got all of your stuff here too. Yeah. So anytime you want to come in, I don't know if you remember a few weeks ago we made those folders. So I keep all of your tests in the same folder. So you can come in and be like, hey, can I just see my folder? And then I can just give it to you. You can look through it all. Yeah. Yeah. Does that make sense to everybody? Okay. So again, if you wrote a 5 on any of that, right, like my version of a 5, then you need to make sure that you're coming in to sit down so that we can go through things. If you got a 7, I want you to do that as well, just because it's good practice. Remember that a 7 will go up to an 8 with complete corrections. A 5 will go up to a 7 with complete corrections. Okay, so it's all in your best interest, both learning and grade-wise. Questions for me? All right, let's do standard 2.2 then. I've got lots of stuff to talk about today, so we're going to just kind of power through and do as much as we can in this Friday morning that we have together.
Can I go to the book?
You may, yes. So standard 2.1 was all about the ideal gas law. Remember, that was that PV equals nRT thing. And we said that that was an equation of state. Which means that it's talking about very specific points in time. What are the pressure, volume, and temperature of a certain number of moles of gas at this moment? Okay. Standard 2.2 starts to focus on how do we change between states or between situations here. So that's 2.1. That's what we've done already. 2.2, we're going to talk about, like I said, the transitions between those. That's really our focus. So there are a few terms that we need to define, a few concepts that you're familiar with that we need to kind of redefine in terms of AP Physics 2 and in terms of thermodynamics. So let's just jump in and do it. The first one that I want to start with is the term heat. Do y'all know what heat is? I feel like we talked about it a little bit a couple of days ago, maybe a few days ago now, at the very beginning of our conversations.
Transfer of energy.
Yeah, absolutely. Transfer of energy, and a specific kind of energy.
Infrared.
What did you say?
Infrared. Or
I mean, that's what, yes, that is another way to say it. Absolutely. Yeah. So it's a transfer of, we often think about it as infrared because that's like the heat energy that we've got, right? Yeah. So, but I'm going to go ahead and say thermal. Is that okay? So it's a transfer of thermal energy. Okay. It's marked with the letter Q. I don't know who picked the letter Q. I don't know why that is, but that is what it is. Okay. What was that?
Well,
there you go. I don't have any good story about why it's that way. It is what it is. Heat always flows from blank to blank. One of the things is cold, one of them is hot. Which way does heat flow? Do you know? We have a vote for hot to cold.
I would agree with that.
Would agree with that?
Yeah.
Can you talk me through why we think that heat flows from hot to cold?
The two objects want to reach equilibrium, so the hot object transfers energy to the cold object until they have the same amount.
Yeah. So you're bringing in the next little idea there. Let me write that word down, and then I'm going to come back to this one. So we are trying to get these two systems or these two objects to reach thermal equilibrium. Okay. Thermal equilibrium is kind of like an equilibrium of forces. Equilibrium of forces means that we're balanced. Thermal equilibrium, as we were kind of saying there, means that they have the same temperature, the same energy. Okay, internal energy, we'll say. We're going to define that in just a second. Okay. So an object that has a higher temperature has more energy in it, right? Okay, because remember we talked about this before, those molecules are moving around much more. And so all it's doing is it's transferring some of that energy to the thing that was cold. It doesn't really make sense that if you have a lack of something that you're able to give it up, right? So it doesn't make sense that the cold would give energy to the hot. That doesn't work. So it's always hot to cold, or we could say from high temperature to low temperature. Okay. Feeling good so far? Okay. Got a little question for you to look at. Then we'll keep defining words. This stuff is pretty straightforward, but I want to make sure that we're feeling really good with it here. Okay. Take a peek. 2 sealed boxes of equal volume contain equal amounts of the same ideal gas. The gas molecules in box A move with twice the speed of the gas molecules in box B. When the 2 containers are brought into thermal contact, so that just means that they're able to transfer energy, right? That heat is able to flow, okay? Which direction will the thermal energy flow? Box B to box A to box B. There's no flow because there are equal amounts of gas. Molecular mass of the ideal gas must be known in order to answer the question. What do you guys think? Should we vote?
Yeah.
Let's vote. Is everybody feeling like they have an answer? Huh? Want to make sure. Are you feeling like you have an answer? Maybe? Do we think it's A, that the thermal energy is going to go from box A to box B? Okay, that's like a lot of hands, like all the hands, 100% of the hands. You think it's A? Why do you think it's A, Olivia? Yeah. I'm going to just say that out loud and make sure that I'm understanding what you said. So you said box A has molecules that move with twice the speed. And if they move at twice the speed, you're saying that if the velocity is higher, that means that the energy is higher, right? And if the energy is higher, you think that the temperature is higher. And so then we can kind of use that idea of heat flow. Go.
Is temperature the average speed of the molecule?
Temperature is related to the speed of the molecules, but it is not the speed of the molecules. So last week, we talked about the internal energy of a molecule, right? We said, I can't remember if we called it, I think we probably just called it K. And we said that K was equal to 3/2 nRT. Do you remember that?
Oh, yeah.
And then you can also say that K is equal to 1/2 mv squared. So you can see that there's a relationship between the velocity and the temperature.
Is K
K is like the kinetic energy of the molecule.
Yeah, wait. Okay, that makes sense. I had a question that I just forgot. I'll tell you.
Let me know as soon as you know it. Yeah, that's totally fine. Okay. All right. So here's the key, friends, is that heat is the transfer of energy, not to be confused with the internal energy of a system. So the next thing that we have to talk about is the internal energy of a system. And that is called literally the internal energy. Okay. And I said it, but I'm going to write it down just for clarity. Okay. Is the total amount of energy of all the molecules in a system. Okay. It's marked with the letter U. Give me just a second, David. Let me say one thing and then I'll come to you. Is that okay?
Yeah.
You have seen the variable U before, I think. Maybe some of you, I should say. In AP Physics 1, we use U to denote, do you remember what it was?
Potential energy.
Potential energy. So it's the same U, But instead of just calling it potential energy, another way that you can talk about potential is stored energy or energy within a system, not energy necessarily of something because it's moving. So that's what we're going to talk about here. Okay. So for my friends that did general physics last year, you're like, I don't know what we're talking about. This is literally what we use to mark potential energy. Oops, I need an E in there. Hold on. That you guys probably use like E sub P or E sub G, right, for like the gravitational energy or whatever. So this is just like the potential or the stored energy in a system. That can be because of its location. So like I've got my frog, and my frog is a certain distance above my table. It's got some stored energy, gravitational energy based on its position. It's also got stored internal energy that's dependent on its temperature. Okay. So I'm going to say one more thing, and then I'll come to your question. Is that okay?
Yep.
So we can calculate this, and we're going to do it using what I just had kind of mentioned, but just to be completely clear about it. So the energy of one molecule is 3/2 kT. Okay, that's the Boltzmann's constant. So then we can expand that out, and we can add up all those molecules together, right? And so then we're just going to call that the internal energy of a system. So this is one molecule. But then if we add up all of those molecules together, we can say that that's 3/2. Well, we're going to add them all up. So it's going to be all the molecules, that's big N, times Boltzmann's constant times time. Or not time, excuse me, temperature. Wrong T. Or we can write it in terms of moles, 3/2 nRT for temperature. So these two expressions are completely equivalent. Okay? This is the total internal energy of the system. The expression over on the left is the internal energy, or is the energy of one molecule. So we're just adding up all of them. Okay. And then the clever thing that we can do is, since we know that PV also equals nRT, we can put these two things together and say that the internal energy of the system also, you could say, is equal to 3/2 PV. Does that feel okay to everybody? I think, I don't have my equation sheet in front of me. Do you guys have your equation sheet in front of you? Let's look and see what's on there. Make sure that we see these on there. I took them out. So on your equation sheet, it does not include either the ones in the rainbow box or in the pink. They do include this one, the 3/2 kV times T. And they do include PV equals nRT. So it's one of those truths, right? Like they could write an entire book with all of the iterations of how you could combine all of the equations. We're not going to do that. So you might want to make a note of that, or just be aware that these two relationships are not listed, but they are still legitimate. And the hints and the breadcrumbs are there. It's just not all of the pieces together. All right, David, what was your, do you have a question too?
So it's 3/3, and that's supposed
Oh, 3/2. Yeah, sorry. Thank you. It wouldn't make sense to be 3/3, would it? Thank you for catching that. I appreciate it. David, you had a question. What was your question?
Oh yeah, it was about the temperature and velocity thing.
Oh, okay.
So if you have two cubes of the same density and the same temperature, and one was bigger than the other, would the bigger one have slower moving molecules?
Say that again.
If you have two cubes,
Two cubes.
so cube A is 2 times bigger than,
Like the volume is 2 times bigger?
yeah.
Or the mass is 2 times, like obviously, right? All of those things are 2 times bigger. Okay. But they're made of the same stuff.
Yeah.
So
if they have the same temperature, are the molecules in cube A moving slower than cube B?
No, they're moving the same speed, but there's more internal energy in A because it's bigger.
Would they be moving slower if cube A has bigger molecules?
Yes.
Okay.
Yes, that's the key. Is that if the masses are different, then the velocities are different. But if it's the same material, then it's going to be the same velocities. Yep. Yep. All right, we got some examples to take a look at here. Oops, we did that one already. Let's look at this one. I think this one might be similar to what your question was, but I can't remember exactly. So let's take a look. I just don't remember this question exactly, but we'll take a look. All right, so we got two boxes filled with molecules of the same gas. So this is kind of what David was asking. Their relative volumes and temperatures are given. The question says, which one contains more internal energy? So go ahead and take a look at that. Talk to your buddies here for a second and see if you can figure it out. The temperature is different and the volume is different. Which system contains more internal energy? How do you figure that out? I'll let you talk for a couple of minutes. Then we'll regroup. All right, you guys can all turn your lights off for a second. Here we go. Let's do it. So, why is this one tricky? And I don't mean that in like a what's your problem sort of way, but there is some stuff in here that seems a little bit weird. What's going on? Yeah, go ahead.
You don't know if the amount of gas is the same.
Okay. So it says that it's filled with molecules of the same type of gas. So I would assume that it's the same density, like there's the same amount of stuff in it. Does that make sense, like per space? So if that's true, how does the number of molecules in A compare to the number of molecules in B?
Wait, are you expanding, is it like the same container expanding or is it separate?
So again, this is what I just said.
Sorry.
Both systems are filled with molecules. So they're filled, we would assume, to like the same density.
Oh, okay.
Yeah, same density, same pressure, essentially. So if how does the number of molecules in A compare to the number of molecules in B?
You would have 2 times more.
2 times more in B, right? So Na or 2Na equals Nb. Does that make sense? Okay. And I care about that because we're trying to find internal energy. The expression for internal energy is what?
3 halves nRT.
Okay. Is that making sense? Okay. So if we know about N, R doesn't change, 3 halves doesn't change. How does the temperature of A compare to the temperature of B? It's a fourth. Okay. Temperature A. Did I write that right? Or did I write that backwards? Did I write it backwards?
It's just 4 times TA.
Hold on. Let's back it up here. Let's do it this way. So the Na is less than Nb, right? So we can say that 2Na equals Nb. Are we okay with that? Okay. In terms of the temperature, we can say that the temperature of A is greater than the temperature of B. So the temperature of A, what is it, 4 times the temperature of A is equal to the temperature of B? Okay. That's not right. That's backwards. How did I write that backwards? Is this one wrong? This one's wrong. The temperature is wrong. 4 times TB is TA. There we go. Right, because TA is bigger. Yeah, multiplication's hard on a Friday morning. Man. Okay. So one of them's bigger and one of them's smaller. Which one's going to matter more? The temperature, right? It's twice as important in its magnitude of difference. So which one has more internal energy? A? Even though it's tiny? Even though it's tiny. Because it's so much warmer. Yeah. Yeah. Did that cause anybody to feel a little uncertain at the beginning of this process? Logan's like, nope, I got this. But there's some people like, yeah, and it's okay. It's all right. That's why we're doing this together. If you already knew all this stuff, it would be silly for us to be doing this together. All right, let's do another one. More examples, more fun. We got 2 more still. All right, let's do a calculation, shall we? A system initially contains 2.3 times 10 to the 20th molecules of a monatomic ideal gas at a temperature of 375 K. Says calculate its internal energy. Plugging in some numbers. If you need to borrow a calculator, go borrow one. I will get your equation sheets out here too, so you can do that as well if you want to. So, we got an answer? What'd you get for an answer, Ethan?
1.07 times
1.07 times
Or no, yeah, no.
times 10 to the what?
24. So
Units are? What's that?
They're not.
Internal energy is going to be joules. Do we agree? I have some dissension over here. What are you advocating for? 1.79 joules?
I got 0.79.
0.79 joules? What'd you guys get over there, Kelsey?
1.29 times 10 to the 25 joules.
Okay. Should we go through this problem? Okay. Did you guys get some? Okay. So at least these 4 people agree. Let's do this together. Here we go. Because apparently there's some disagreement. We're going to do this in like the straight up guess method. Here we go. So what do we know? We are given 2.3 times 10 to the 20th molecules. What is that? What variable is that? Big N. Right? Number of atoms. Number of molecules. Okay. What else do we know? We know the temperature is 375 Kelvin. Anything else we know? We know Boltzmann's constant, I hope. Right? Boltzmann's constant, I always have to look it up because I don't have that one memorized. So I don't use it very often. K sub B is 1.38 times 10 to the negative 23rd joules per Kelvin. Part of the reason we love it is because we can double check our units to make sure that we're doing this all right. Okay? All right. And the equation that we're going to use is U is equal to 3/2 capital N K T. Yes? Everybody good? Okay. So let's do this together. I want, because we got lots of different answers. So I want everybody to plug this in, but we're going to do it together. So we're going to do 3/2 times N. Did I do something wrong? Oh, okay. Fair enough. 2.3 times 10 to the 20th, that's molecules, times K, which is 1.38, times 10 to the negative 23rd, joules per Kelvin, times 375 Kelvin. I want every single person to plug this back into your calculator. I would do it in lots of steps, but you can do it however you want. I just want to make sure that you're successful. Everybody do it. How are we doing, friends? Got some stuff again? Plugging all these things in. And it really doesn't hurt to take it step by step, to write down your givens, to write down your equation. I know it feels like we did that last year. I know, but we'll do it again. Let's do it now. Because we don't want to mess up silly things like this. What'd you get for an answer? Okay. Does that feel better? Is that what you guys got? Yeah? Yeah? My friends in the back, did you get this?
Yeah.
Excellent. All right. We are going to do one more problem. Here it comes. Brace yourself. A system initially contains 2 moles of a monatomic gas at a temperature of 90 degrees Celsius. Its internal energy is U. The system is then cooled to half its original temperature, I'm reading that correctly, 45 degrees Celsius. What is true of the new internal energy? Give you just a couple moments to take a look at that. Turn those lights off right now and then turn them back on when you are ready to discuss.